Yo, what's up, people? Um, welcome to another day of physics. So you all went through this problem for homework. You've already had a few minutes to look over your solutions, and I'll show you my solution. We'll see how you did. So record player spins at 33 RPM. Diameter is 30 centimeters. What's the linear speed of a piece of dust on the edge of the record? So I always like to start with a diagram. Here's the record. Here's our piece of dust. And let's see. What I usually like to have are things like this are, let's say it's going around this way, sure. It's the linear speed. So that linear speed, we're really asking for what we call tangential velocity. Same thing, 2 pi r over t. Can't you just do pi d over t? Sure you can. So we have d, which tells us r, but we don't have, well, let's see. For the period, we have this. 33 revolutions per minute. Well, hopefully you recognize that that's actually a frequency. 33, I'm going to write it like this. Revolutions per minute. Okay, therefore, the first thing I'm going to do is, especially if we want this in meters per second, I'm going to turn this into revolutions per second. So to do that, I'd say that in a minute, there are 60 seconds. So this turns into 33 divided by 60, 0.55, our frequency, 0.55 hertz. From that, I can find the period by just doing 1 over the frequency. So I do the inverse of this, and I get 1.8, let's call it 1.82 seconds. Okay, now I can come over here and say that V is 2 pi times, well, check this out, 0.15 meters. That's in centimeters. All right, I took half that diameter. You could leave it as diameter. Here's diameter, 2 times r, right? And divided by our period, 1.82 seconds. V is 0.3 times pi divided by 1.82, 0. Let's call it 52 meters per second. Okay? Okay, now some of you might notice that working with V is 2 pi r over t, well, since frequency is 1 over period, this is the same as 2 pi r times 1 over period. This is actually the same thing as just doing 2 pi r times the frequency. So if you want to eliminate the step of finding the finding the period, you can just do this, 2 pi r times f. Okay? Okay. Next example. Number 3, piece of clay moves with that speed on a potter's wheel. Piece of clay, blah, blah, blah. How many times will it pass the potter each minute? How many times will it pass the potter each minute? We're looking for a number of revolutions per unit time. We're looking for a frequency here. Frequency equals question mark. Well, we know that V, I forgot, I guess I kind of broke my rule here about, sure, diagram. Here's the wheel, here's the clay, cruising around like that. Here's the radius. I don't know how much that helps. Well, here's the thing that actually does help a bunch from the last page. We said that we can also write this as 2 pi rf. And especially here, since we want the frequency, well, that makes sense to do. So I'm going to write it as f is v over 2 pi r, or 2.5 divided by, 2 pi times 18 centimeters. It does say the piece of clay is 18 centimeters from the center, so that is the radius, 0.18 meters. Parentheses for all you folks that Have trouble with that. 2.5 divided by parentheses 2 times, come on, pi times 0.18 close parentheses. So I get a frequency of 2.21. Well, that's hertz, right? Notice we end up with a per second there. All right, but we want it per minute. Well, I would say this is 2.21 per second. If we want it per minute, there are 60 seconds in a minute, so we multiply our answer times 60. 100 and let's call it 33. Okay? 133 revolutions, really revolutions per minute. Fair enough? Okay, now, whoa! What happened to, what? Don't look, don't look. Close your eyes. Close your eyes. Close your eyes. Why'd that happen? Go back. Yeah, what? No! Don't look. Okay, now you don't have this page. So, yeah, all right, you don't even have this page. What we're going to do here is derive two equations. One equation that tells us how to calculate centripetal acceleration, and another one that tells us how to calculate centripetal force. This is kind of a confusing derivation, so I didn't bother giving you the slide. I'll tell you what to write down at the end, okay? But yeah, we're going to first find acceleration, or an expression for how fast something changes velocity when it's moving in a circle. All right, so what we're going to do is, let's say we look at an object that starts with that velocity, v1. Sometime later, it has this velocity, v2. Sometime later, it has that one, and sometimes later, it has that one. And it goes back to v1, and so on, and so on, and so on. All right? Well, what you might remember is that if we're trying to find acceleration, I'm going to write that up here, we have to do change in velocity per unit time. Right? Sure. So what's the change in velocity? Well, if we want to figure out how much it changes from, say, v1 to v2, we actually do this. So this is going to be confusing, I get it. This is, notice, here's v1 going this way. So this is actually vector negative v1. And since we're adding these tip to tail, this is v2 plus negative v1. Or it's v2 minus v1. And remember, if we want to do a change, a delta v, you always do the final minus the initial. So that's what we're doing here. We're doing the final minus the initial. We're doing it as final plus negative initial. And the resultant of those two vectors is this one. That vector is a change of velocity from velocity 1 to velocity 2. Right? Might be one of the harder parts here. Now, we can get the same vector. I told you never to do this, but if we draw them tail to tail and draw that vector, notice how this one and this one are the same vector. So what we can do is a little shortcut here where we just draw these all tail to tail and combine the tips or connect the tips, and we get all those changes. Well, if we want, you know how just with the way we find velocity, we look at the whole loop and you sort of use the period. For velocity, remember, we would say, okay, it goes all the way around. The distance we use is circumference, and then we use the amount of time, t. Well, we're going to sort of do the same thing here. We're going to say, what's the total change in velocity in one period? Well, the total change in velocity would be the whole perimeter of this square. We take the length of those things and add them up. All right? But here's the dealio. There aren't really just those 4 velocities, v1, v2, v3, v4. They're really more closer to 8. Well, they're really more like 16. They're really closer to like, well, they're really an infinite number of those. All right? So if we take the total of all the, what do you call it, delta v's, well, the delta v's are all these little vectors now. The total delta v is the circumference of this circle. And the total delta t, well, is what we call the period. But here's the real tricky part. The radius of this circle is made of these velocity vectors. So it's really 2 pi times v over the period. And v really is 2 pi radius of the actual circle that it moves in divided by the period. Are your eyes bleeding yet? So that means, just doing some math here, 2 times 2 is 4, pi times pi is pi squared. Well, there's an r by itself, and then t times t is t squared. There's one way to calculate centripetal acceleration. What you might notice is this kind of almost looks like we took, well, v is 2 pi r over t. If we just square everything, you get 4 pi squared r squared over t squared. And it almost looks exactly like this, except notice there's only one value of, or one factor of r there. So if we do this, it gets rid of one of those. So the real thing you have to be able to do is, or that you really should be familiar with, is this one. The thing in the middle is not as important, or it's more rare that you would do that because that one's not in the reference table. This one's in the reference table. All right. Doing it this way in green just says that you're not going to find v by itself. That kind of lets you do it all at once. But if you can do a is v squared over r, that's the real important thing. All right, you got to write that down. AC is v squared over r. Then you might want to check at some point in the back of your reference table and make sure you can find that. Centripetal acceleration is v squared over r. All right, you're going to have to use that today. Now, the centripetal force thing is a lot easier because force is just m times a. So all we do for that is m times, well, a is v squared over r, so force is m v squared over r. All right, that's the other. Actually, I don't think that's in your reference table. It does. I think this part's in your reference table. Maybe. Let me check. No, it's not. They assume that you understand that F equals ma. All right, but if you go from force to this mv squared over r, that's going to be a real important part for you. Okay? So those are the things you need to write down. I'll be as clear as I can here. 1, AC is v squared over r, and 2, FC is mv squared over r. Those are the big two equations you'll need moving forward. Really the only, well, I guess along with this one, v is 2 pi r over t. That's new stuff. Oh, I guess and period is 1 over frequency, so there's quite a bit of stuff. Okay? Let's see. Another video to come in a few minutes. Yeah. So, that's interesting. I'll tell you a stupid story about it on Friday. All right. Later, folks. Later, Hosen. Yeah, later, Hosen. See ya.